Good afternoon, my student. Welcome to another chemistry lesson. And in today's lesson, we are going to discuss titration, but specifically on double indicator methods. Is it okay? So welcome. It's a very interesting lesson. It will take about 40 minutes. So welcome. But before I continue, I have to show you the chemical reagents that I have with me here. So please let me start from my right here. I'll start from my right here. So I have this solution labeled as solution B, and this is a mixture of sodium carbonate and sodium hydrogen carbonate. Is it okay? Then another solution here labeled as solution A. This is a hydrochloric acid solution. You can see, and the molarity is 0.2 molar. 0.2 molar solution A. Then I have two other solutions. These are indicators. We have methyl orange indicator with a dropper. Then we have phenolphthalein indicator with a dropper. So these two solutions are normally used using a dropper. Is it okay? Without wasting time, I have apparatus also. I'll be able to take you through later. But meanwhile, let us focus on the board for 1 minute. Let us focus on the board for 1 minute. On my board here, I've written titration, but as I have said, this specifically double indicator method. Is it okay? Then this is experiment 1.3, and the aim of this experiment is to determine percentage of sodium carbonate and sodium hydrogen carbonate in a mixture. And you have been provided with the following: 0.2 molar hydrochloric acid as solution A. Then you have solution B, and this solution B contains 10.3 grams of a mixture of sodium carbonate and sodium hydrogen carbonate. Then thereafter, we have the procedure, which I'm going to take you through. And after the procedure, we have two tables here, two titration tables. We have table 1 and table 2. Is it okay? So my student, this is very interesting. In titration in table 1, the final value in this table, the final value in table 1 will be your initial value in table 2. That one will be your initial value in table 2. Are you getting? So follow me and see how it is very interesting. Is it okay, my student? So without wasting time, let us proceed to the procedure. The first procedure, my student, and ensure you look at what I'm doing, my student. Focus at me, and you also focus on the chemicals. So in procedure number 1, I want to take solution A, which is 0.2 molar hydrochloric acid. Then I fill the burette. Is it okay? That's procedure number 1. And as I say, I do it. And you also follow me. Is it okay? Let us go. So I want to fill the burette. So I'll take the funnel, then focus on the top of the burette. Focus on the top of the burette. I place there the funnel to help us fill solution A into the burette. Is it okay? Thank you. So let us fill the burette to the 0 mark with solution A, 0.2 molar hydrochloric acid. So my student, you focus my student. Then I have to reduce to 0 the excess one. Let us see. So it is on the 0 mark, and always my student, you read below the lower meniscus. You read below the lower meniscus. Is it okay? That was procedure number 1, filling the burette with solution A. Procedure number 2, I take a pipette and a pipette filler. Is it okay? So that I'm going to pipette 25 mils of solution B into a clean conical flask. Is it okay? Let us go. So I have to transfer solution B, which is a mixture of sodium carbonate and sodium hydrogen carbonate. Then I pipette. And remember, nowadays we don't use our mouths to suck the chemicals in the pipette. We use what we call a pipette filler. It is for our healthy reasons. Is it okay? Let us go. So I'm pipetting 25 mils of solution B. Solution B, 25 mils. So this is exactly 25. Then I transfer into a clean conical flask like this. So I've transferred solution B in, and the volume of solution B is 25 mils. Is it okay? Then we have been talking of double indicator method. I've been talking of double indicator method. So double indicator method means we are going to use 2 indicators. And in this case, I'm going to start using phenolphthalein indicator. Is it okay? And as I titrate, I fill table 1. So follow me. I'm going to take 3 drops of phenolphthalein indicator using a dropper. Look at the initial color of solution B. It's a colorless solution. Then let me add 3 drops of phenolphthalein indicator. 1, 2, 3. So I've added 3 drops of phenolphthalein indicator. I've added 3 drops of phenolphthalein indicator. What's the color after adding phenolphthalein indicator? Is it pink? Is it pink, my student? Yeah, you can see it is pink. The color is pink after adding phenolphthalein indicator. Is it okay? It is pink. Let me shake so that you see. Is it pink? Pink, isn't it? So the next step, I'm now going to titrate this solution A in the burette against this solution of solution B. Is it okay? And as I titrate, I have to swirl the mixture or the solution. Then, what do we expect when I titrate? This pink color must turn colorless. By the time it just turns colorless, then I stop titrating and I read. Let us go. And this one, my student, require your patience. So let me start titrating as I swirl like this. These are pink solution, you can be able to see, isn't it? So let us go. So as I titrate, I have to swirl until it will turn colorless. So, and when you titrate, don't be in a hurry. And your focus must be on this pink solution until the time it will turn colorless, isn't it? So you swirl like this as you continue titrating. Can see it is still pink. It is now almost turning. It has now turned colorless. The solution B has turned colorless. You can now see my student. You can be able to see it is colorless now. So if that is the case, then you stop titrating, then you read on the burette. And when I read on the burette, it is 8.9. It is 8.9. The final reading is 8.9. Is it okay? Yeah. So next step I have to record in the table. Is it okay? Table 1. So with me, focus here. Focus here with me. So my student, you can see we have initial burette reading and final burette reading. And we began from 0, isn't it? So the initial burette reading for titration number 1 is 0.0. 0.0. Then the final burette reading, it is 8.9. Is it okay, my student? Then how do you arrive at the volume of solution A used? Remember, solution A is the one in the burette. So you take the final burette reading minus initial. Is it okay? So in this case, 8.9 minus 0.0, this one is 8.9. Get 8.9. Is it okay? Then, my student, what next? I now take this just slowly. Focus here. So the next step, I take this resultant solution, then I add there 3 drops of methyl orange indicator. Then I continue titrating solution A remaining against the same. And therefore, our initial value or volume will be 8.9 from the burette. Is it okay? So the initial value for table 2, we are beginning at that point where we stopped, 8.9. Is it okay? So let me do it. So I've said we are done with phenolphthalein indicator. Now I'm using now methyl orange. I'm using the resultant mixture. Is it okay? So I have to add there 3 drops, and the solution is colorless. It has turned colorless. So let us see what will happen with the color when I add methyl orange. 3 drops. Let us go. 1, 2, 3. Only 3 drops. Then I have to swirl. Have to swirl the mixture. So that you can observe which color has formed from colorless to yellow. Are you able to see the yellow? Are you able to see the yellow? Is it clear? So the solution, when you add methyl orange, it is yellow to the mixture. Then I continue titrating with this solution A. So when I titrate, I'll titrate until the yellow color turns orange, closer to orange. Is it okay? Let us go. And as you titrate, you have to swirl the solutions. So I have to swirl like this. So I titrate, I have to swirl. You can see the solution is still yellow. You can see the solution is still yellow. The solution is still yellow. And as you titrate and swallowing, it means you swallow like this. I'm sure you see the way I'm doing it, isn't it? I think it is clear like this. This is what we mean by swallowing. The solution is still yellow. Oh, it has just turned immediately to orange. The end point has been reached. Now using methyl orange. The end point has been reached. Then I have now to read on the burette. Let me see. This is 22.9. It is 22.9. It is 22.9. So focus, my student. Just be slow and focus. So I said, when now you use methyl orange, we move to complete now table 2. But remember, we are still on titration number 1. We have not moved to titration number 2, isn't it? So the initial burette reading for table 2, I said this one, the final burette reading for table 1 become our initial burette reading, which is 8.9, isn't it? But the way we have been titrating, the final burette reading we have found out is 22.9. Is it okay, my student? Then, how do you get now the volume of solution A used in centimeter cube? Remember, solution A is in the burette. So solution A is there in the first table and in the second table. We are just using solution A all through, isn't it? We are just interchanging, we have just changed the indicators. Is it okay? So you take initial final, which is 22.9 minus 8.9. This one gives us what? This is 14.0. Is it okay? 14.0. Then my student, you can now take another clean conical flask. You again pipette solution B, 25 ml. You add there 3 drops of phenolphthalein indicator. Then you refill the burette to the 0 mark. Then you repeat the procedure. And then again you fill the table 1 for titration 2 and table 2 for titration 2. When you finish, you take another clean conical flask. You pipette again 25 ml of solution B. You add phenolphthalein indicator, you fill the burette to 0 mark, you titrate, you fill table 1, you add methyl orange, you fill table 2. That's titration 3. Is it okay? So my student, without wasting time, if you do it very carefully, let us come here to titration number 2 in table 1. So you fill the burette so that from time to time you are starting from 0.0. And for consistency reasons, my student, the results are very close. And I normally advise that just give or titrate and ensure that the values are uniform. Is it okay? So here you will also land on 8.9 as the final value. 8.9. Then when you subtract the final minus initial, you will also get 8.9. Then for table 2, titration 2, we said that the final value in table 1, now that one becomes our initial value in table 2. 8.9 is our initial. Then if you titrate from 8.9 using middle orange, if you are very careful, you will land on the same 22.9. Is it okay? Then when you take the 22.9 minus 8.9, then the volume of solution A used in the second table will remain 14.0. Then again you fill the burette to 0 mark and you repeat the procedure so that always in table 1 you are starting at 8.0. Then when you titrate using phenolphthalein indicator, if you are very careful, you will again land on a value close to 8.9. Is it okay? And then when you subtract the final minus initial, you get 8.9. Is it okay, my student? Then table 2, when you now add middle orange, we said the final value in table 1 become your initial value in table 2, which is 8.9. Which is 8.9. Is it okay, my student? Then when you titrate using middle orange very carefully, the final value will be also close to 22.9. Then when you subtract final minus initial, we land on 14.0. This is for consistency reasons. So my student, without wasting time, this is what we normally consider after completing the table. During marking, we look at complete table, we earn your mark. Decimal place, we earn your mark. Accuracy, we earn your mark. Principle of averaging, we earn your mark. That is for table 1. Then for table 2, the same. Complete table will earn your mark. Decimal place will earn your mark. Accuracy mark will earn your mark. Principle of averaging will earn you another mark. Is it okay, my student? Then the second step is now on calculation of moles. Calculation on moles. And calculation on moles are very simple. You just know the formulas and just apply them. Is it okay? Let us go through and see how simple it is. And hope you are following, isn't it? And you are enjoying. Good. That is just to make you active, isn't it? To make you concentrate. Okay, let us continue. We are now in calculations. Number 1, that is number 1. Just focus. Let us take this one as question A. Because the table we have already completed table 1 and 2. So question A, determine the volume of solution A needed for phenolphthalein endpoint. So average volume for phenolphthalein endpoint, that's in table 1, isn't it? So average volume, you focus, my student, and see how simple it is. You go back to table 1 where we used phenolphthalein indicator. We have 3 titration. So volume of solution A used is here. So that you add the 3 titrations, then you divide by 3. Is it okay? And we do it. So that is 8.9 plus 8.9 plus 8.9, then divided by 3. This one gives us 8.90 centimeter cube. And I put there tick. Is it okay, my student? Then Roman 2, the volume of solution A needed for methyl orange endpoint. So that's the average volume now in table 2, my student, where we have solution A used in methyl orange. We take volume for titration 1, 2, and 3, and because there are 3, then we divide by 3. And during averaging, we look at consistency, and you can see my values 14.0, 14.0, 14.0. Is it okay? So I can use them to average. So just say average volume is equal to 14.0 plus 14.0 plus 14.0. Then I divide them by 3. This one gives me 14.00 centimeter cube. And I put there a tick. Is it okay? Then we want to move to question B, and follow me to the other side. And I have to remove this. So focus, my student, and see how simple it is. And I hope you are focusing, isn't it? And please enjoy the lesson. So, question B, determine volume of hydrochloric acid required to neutralize Roman 1 sodium carbonate in 25 centimeter cube of solution B. So, my student, here we have this formula V1 times 2. We take V1 times 2. Then what is V1? V1 is the volume in table 1. Is it okay? The volume in table 1 is V1. So that V1, we have found out. Is it possible to focus, my student, so that I can show you in table 1? The volume of solution A used, we take the average of 8.9 in the 3 titration, and we have found out V1 now becomes 8.90. Is it okay? So you take 8.90 times 2. This one gives us what? Using my calculator here, I take 8.90 times 2. This one becomes 17.80 centimeter cube. 17.80 centimeter cube. Is it okay? Then you have to determine also the volume of hydrochloric acid required to neutralize sodium hydrogen carbonate. So in this case, you take V2 minus V1. So what is V2? What is V2? I can take you back here slow by slow, my student. So the volume, the average volume in table 2, the average volume in table 2 becomes our V2. Is it okay? So let us go back slowly. So our V2, the average volume is 14.00. Then we minus V1, which we have found in table 1, the average volume is 8.90 So if you subtract 14, you take 14, you subtract 8.9. 14 subtract 8.9. This 5.1. This one becomes 5.10 centimeter cube. So that's the volume of sodium, the volume of hydrochloric acid that reacted with sodium hydrogen carbonate. Is it okay? And hope you are well focused. Is it okay? Then we move on to the second question. From values in B above, from values in question B above, calculate from values in question B above. I can remove this one. From values in B above, calculate Roman 1, number of moles of hydrochloric acid which reacted with sodium carbonate in 25 centimeter cube of solution B. So here, my student, it is very simple. Number of moles is given by this formula as usual. Molarity times volume all over 1000, where 1000 is the volume in 1 liter. Is it okay? Good. Then we ask ourselves, what is the molarity of HCl, capital M? We go back to the informations provided. Is it okay? So focus just slowly, my student, and see. From the initial information, you see you are provided with 0.2 molar hydrochloric acid solution. So hydrochloric acid is molarity 0.2. Is it okay? 0.2. So you just substitute, that is for M 0.2 times. Then we ask ourselves, because they are saying number of moles of hydrochloric acid which reacted with sodium carbonate in 25 centimeter cube of B. But in question B, we have found out that the volume of hydrochloric acid required to neutralize sodium carbonate in 25, we have found out it is 17. We have calculated it is 17.80, isn't it? So the volume of the acid is 17. That's from B, 17.80. Then all over 1000. Let me write properly 1000. So you take now the calculator and follow me. So that is 0.2 times 17.80. Then I divide by 1000. That gives me 0.00356 moles. Then I put a tick. Is it okay, my student? So we move on. Is it okay? And I hope you are enjoying my student. And at the end, you will realize that calculations on titrations, the moles, are very simple if you follow the instructions step by step. So let us go. So now Roman 2, you calculate the number of moles of sodium carbonate in 25 centimeter cube of solution B. Is it okay? Then here, my student, if you want to know the number of moles of sodium carbonate in 25, which we pipetted, is the same number of moles of sodium carbonate, or the number of sodium carbonate which reacted with solution A in the burette. Is it okay? So we need to get what we call the mole ratio, and the mole ratio we require to write the chemical equation for that reaction. So let us go. So it is sodium carbonate, solution B, reacting with dilute hydrochloric acid solution A in the burette. So this one gives us a salt, carbon dioxide in water. So the salt is sodium chloride plus carbon dioxide gas plus water liquid. Then you have to balance the equation to get the mole ratios. So when I look at the reactant side, I have two sodium atoms. Then we have one sodium atom on the product side. So I have to put here 2 to balance. Then chloride becomes 2 on the product. So I have to balance chloride on the reactant side. So I also put here 2. And therefore you can see now that the equation is balanced. You can check and see. Then the mole ratio now between the carbonate and the acid, it is now 1 sodium carbonate reacting with 2 moles of hydrochloric acid. So the mole ratio here, mole ratio between the carbonate and the acid is 1 to 2. Is it okay? So these 2 is for the acid, and we have found out that the number of moles of hydrochloric acid which reacted to sodium carbonate is 0.00356 moles. So this means this ratio 2, we talk of if 2 is giving us 0.00356 moles. What about the carbonate, which has ratio 1? So you say then ratio 1 will give us which moles? So this is about now cross multiplication. Is it okay? So what you do, you now take 0.00356 divided by 2 times 1. This one, when I take my calculator, that one gives me 0.00178 moles. Then I put a tick. So it means these are the moles of sodium carbonate. Number of moles of sodium carbonate in 25 centimeter cube of solution B. Is it okay? Using the mole ratio between the carbonate and the acid, the way we reacted, isn't it? Good. Roman 3, question Roman 3. Hope you are focusing, my student, isn't it? Calculate the molarity of sodium carbonate in solution B. Molarity of sodium carbonate in solution B. So it is very simple. We apply the formula. We have this formula, my student, which says molarity is equal to number of moles times 1000 all over volume. Do I know the number of moles of sodium carbonate in solution B? Yes. We pipetted 25. Isn't it? 25. So the moles we have calculated of sodium carbonate is this one, 0.00178. So what I do, I just substitute the information. So the moles are 0.00178. 1000 is a constant. which is the volume in 1 liter of solution, isn't it? Then I divide by the volume. The volume of sodium carbonate which we pipetted, I pipetted, just wait, I show you. I pipetted 25 mils. So that's the volume of sodium carbonate solution B. Is it okay? So I have now to divide this one by the volume, the volume, which is 25. So when you calculate carefully, the molarity becomes 0.0712. To show it is molarity, you put there capital M, of what? Sodium carbonate. Is it okay? Then my student, we move on to question D, and hope you are focusing well so that it is clear. So from your values in C3, which is the molarity, in C3 it is the molarity of sodium carbonate. So they are saying from your values in C3 above, calculate the mass in grams per liter of sodium carbonate in solution B. So you have to calculate the mass in grams per liter. But remember, we have this formula here which says molarity. We have another formula which says molarity is equal to mass or concentration in grams per liter all over RFM. So, how do we now get the mass in grams per liter? We make this one the subject of the formula, isn't it? So that if we want the mass or concentration in grams per liter equal to molarity times RFM. Do we know the molarity of sodium carbonate? Yes, we have calculated. It is here. Is it okay? So I just substitute there where there is molarity 0.0712. Then times RFM. RFM of sodium carbonate, we have been given relative atomic masses of this atom. Sodium is 23, carbon is 12, oxygen is 16, isn't it? So to get the RFM, we add the individual relative atomic masses. So sodium has 2, there are 2 here in the carbonate, so that is 46 plus 12 for carbon, that's 58. Then plus 48 for 3 atom of oxygen, that is 106. So RFM is 106. So times 106. So if you calculate, my student, very carefully, times 106, you get 7.5 grams. And these are grams per liter. Is it okay, my student? Then I put a tick. Then the last question, my student, hence determine the percentage by mass of sodium carbonate in solution B. Percentage by mass of sodium carbonate in solution B. Remember, in solution B we have a mixture of sodium carbonate and sodium hydrogen carbonate, isn't it? Let me take you back to the initial information provided. Slowly, please, slowly. Then you have been provided solution B containing a mixture of sodium and carbonate and sodium hydrogen carbonate. But the total mass of the mixture is 10.3 grams. Is it okay? So we want to get the percentages of sodium carbonate and sodium hydrogen carbonate. So let us see. So the mass of sodium carbonate in grams per liter is 7.5. So you talk of percentage mass of sodium carbonate in the mixture. Sodium carbonate in the mixture is given by 7.5 all over 10.3 then multiplied by 100. So if you calculate carefully, times 100, that is 7.5 times 100 divided by 10.3. This one gives me around 72. When I round off, the whole number is 73. This is 73%. 73% of sodium carbonate in the mix. What about a percentage of sodium hydrogen carbonate in the mixture? Is it okay? So you just take 100% minus 73. This one gives you around 27%. Is it okay, my student? Is it okay? So my student, I want to say something as I finish. So we have two titrations here. Titration number 1, that is in table 1 and in table 2. Table 1 and 2. So in table 1, we used phenolphthalein indicator, but in table 2 we use methyl orange. Is it okay? So the acid in table 1, when you use phenolphthalein indicator, it neutralizes sodium carbonate halfway. Is it okay? Then sodium hydrogen carbonate is unaffected, it remains. But when now we add methyl orange in the second titration, then sodium carbonate, the remaining half, is also neutralized by HCl. Is it okay? Then also, sodium hydrogen carbonate is neutralized in the second titration when we added what? Methyl orange. That's why, my student, when we were calculating HCl that reacted with sodium carbonate to neutralize 25 of sodium carbonate, my student, we take V1 times 2. When you use methyl orange and when we use phenolphthalein, the volume which neutralized sodium carbonate using methyl orange and also using phenolphthalein, it is the same. Is it okay? That's why I times by 2. Then to get now the volume when we of HCl, which neutralize now the sodium hydrogen carbonate, we take now the volume 2, which is 14, then we minus volume 1. Is it okay? Hope you have enjoyed the lesson. Until next time. Thank you.